Hi everyone. Thanks a lot for looking at this talk today. This is a talk about quasi-polynomial time 2 plus epsilon approximation for the planar Sparsest cut problem. It's a joint work with Anupam Gupta, Phil Klein, and Jason Lee. In the non-uniform Sparsest cut problem, we are given a graph G with edge weights W and a set of demand pairs. It's a function for each pair of vertices, it assigns a positive number. And the goal is to find a cut that can be seen as a set of vertices such that it minimizes the following quantity, which is the ratio of the total weight of the edges in the cut divided by the total demand of between vertices across the cut. And here we have the demand that is over all possible pairs of vertices, while the weight of the edges is only on the edges of the graph. It's a very classic optimization problem that has led to many new and interesting algorithmic ideas, from Leighton Rao almost like 30 years ago to the more recent Aurora Rao-Vazirani result. And the picture of this is that for the problem I just stated, in general graph, we know of a square root log n times log n approximation by Aurora, Lee, and Naor. And in planar graph, we know of two results. In the uniform case, where the demands for all pairs of vertices is 1, we know an exact n to the 2.5 algorithm, and we showed that there is no, showed last year that there was no subquadratic algorithm under some popular conjecture, complexity conjectures, and we can get a constant factor in time. But for the non-uniform case, which is the one I stated just before, we only know of a square root log n approximation that is, just slightly better than the square root log n log n that runs in linear time from Rao in the 99. And we know that there is we can't get a p-test, an approximation scheme for the problem, because it's apex hard. So it's 17/16 minus epsilon hardness of approximation, even for 3 with 3 planar graphs, so series parallel graphs. It's very delicate picture here. And an important open question that has been haunting a researcher over the years is whether one can get an R1 approximation for non-uniform Sparsest cut on planar graphs. And arbitrary planar graph, no bound and 3 widths. Can we obtain something better than square root log n? And in this paper, we show that we can actually give a 2 plus epsilon approximation for planar graph with a running time that is quasi-polynomial. So n to the order log squared n with some function of epsilon that I'm gonna ignore for the ease of exposition. Okay, so let me try to give you the key ideas. And one of the key idea is what I like to call a pizza cutting lemma. And I hope you guys are hungry because it's very inspiring. All right, so we have to start with a structural insight on planar uniform Sparsest cut that also carry others for non-uniform case, which is that the optimum solution is a simple cycle in the dual graph. So the dual graph of, for example, this graph that we are seeing right now is obtained by putting one vertex in each face and connecting with an edge adjacent faces. And here we can see that the solution is of optimum solution, let's say for planar Sparsest cut, is this set of red edges that define the cut between the vertices in the center and the vertices on the outer face. And if we move to the dual graph, it defines actually a simple cycle in the sense that each face that has vertices that are on the different side of the cut is going to be on the cycle. And there is an edge connecting two adjacent faces that correspond to the edge between that is in the cut. And so we can work directly on the dual graph. And that's what I'm going to do in the rest of the talk. I'm going to work on G star, what I call G star, which is the dual graph. And the demands now are not between vertices, they are between faces of this graph. because the vertices of the primal become faces in the dual. And each edge of the primal can be associated with an edge of the dual that has, for which we assign the same length. And now our goal is to find a cycle, possibly simple cycle, but not necessarily simple, we'll see, is to find a subgraph, I should rather say. We know that the optimal subgraph is a cycle. That minimizes the following: the number of, the total length of the subgraph, the total weight of the edges, and I'm going to call that length because that's going to be easier. The total weight of the edges on the subgraph divided by the sum of the demands between the faces inside and the faces outside. And that's now our goal for the rest of the talk. Okay, so let me try to give you our general approach, and then I'm going to try to illustrate it and give more details. So one way to approach this is to compute a hierarchical decomposition of the graph. So we start with the whole graph. That's our initial partitioning with one part, the whole graph. And then what we would like to do is compute a partition P1 of this graph G star, the dual graph, the P1, and then compute for each part of P1 another partition, and so on. So that's a recursive partitioning of the input. And one property that we would like to have in this decomposition is that for each partition, if I look at the number of edges of the cycle of op that I'm trying to find, is small. Between the parts of the partition is small. So if I look at the first partition, let's say P1, the number of edges that are one endpoint in one part and the other in another part is small. Okay, why is that interesting? Because if we realize that, if this number is small, if let's say this number was 10, then we could try to have a dynamic program that would say, okay, given these 10 edges, what are the best solutions in each part? And we could try to do this. That bounds the interface between the different parts. So then we could have a dynamic program that goes up, that goes bottom up and solve depending on the interface with the rest of the world. Okay, so that's a very basic approach. It's trying to fit the instance into a dynamic program. Then, of course, the issue we have here is that there is no dynamic program. Even if we have bounded interface between different parts, it's not clear that there is a dynamic program. In fact, what I'm trying to do here is reduce the interface so that the graph looks like the decomposition is like a tree decomposition of the graph that has small tree widths in spirit, in the sense that the number of crossing is small, so it's like having small tree widths. And then what we can do is, if we have a small tree width modelization of our graph or decomposition of our graph, we could use a two approximation for bounded tree width graph from Gupta, Talwal, and Whitmer who gave like a two approximation for this case. And it's using the two approximation is obtained using a Shirley-Adams inspired LP that I will describe briefly at the end. But that's the basic idea, is to try to get few crossings so that we can use the Shirley-Adams machinery to then find a good solution. And in this talk, when I'm going to say small, I'm going to mean something like log squared n or like log n with some polynomial in epsilon that I'm going to ignore. Okay, so like more pictorially, the property I'm trying to achieve is the following. We could find a partitioning of our graph that is modeled with these blue bubbles. Each blue bubble represents one part of the partition. So these four bubbles partition the whole graph. And here, if up looks like this, it's nice because the number of crossing between two blue bubbles is, or between all the blue bubble actually, is small. It's only 6. Okay. Then that's nice. So that's for the top level. And then what I want to do is to have this property recursively. So now if I compute the partition of each blue bubble individually, I'm going to have another partition. And what I would like to have is that between these parts of this new partition, again, the number of crossing is small. So here it's going to be 3. And then that's very valuable. Here it's going to be 3 as well. We are happy. Here 2, we are happy. So that's good. And then I want these to hold for all levels. So again, I'm going to split each of the resulting bubble into another set of now squares, and I hope that between the different squares in that bubble, the number of crossing is small. Of course, what I'm not trying to do is that I'm not trying to bound the total number of crossing between all the green bubble, the green squares, right? Because if I look at all the crossing of the whole graph between the green points, the green parts, that's too many. But if I have this nice hierarchical structure, then it becomes tractable with the shear density P. Okay. So how to find this partition with few crossings? That's the next step. So one tool we're going to use is this result by Abraham, Gaval, Gupta, Neyman, and Talwar that says that given a planar graph, planar metric, and that's why I'm talking about length at length, because we can look at the shortest path metric on this graph. So I'm still working in the dual. And the parameter D, there exists a randomized partition of G, such that each part has diameter at most D, and the probability that I have two vertices that end up in different parts is proportional to the distance between the vertices divided by D. Okay. So the immediate corollary out of this theorem is that for my problem, if the length of opt, so not the length of the whole graph, but just the length of the opt subgraph, is at most xi times the diameter of the graph, then if I pick a diameter divided by 2 bounded partition of this graph, so I reduce the diameter of the graph by 2 by picking this randomized partition like this, the expected number of edges of opt between the different parts is going to be opt divided by the diameter in expectation, linearity of expectation, which is xi. So if xi is not too high, then I'm very happy because the expected number of crossing between the different parts is bounded. So here is a naive approach. Compute the diameter G over 2 bounded partition P. Then for each part, compute the diameter of G divided by 4, so on. And now what we have? We have the following analysis. If opt is at most log n divided by some epsilon times the diameter of G, then the expected number of crossing of opt over the partition I'm computing is small. That's what I just said before. It's in expectation log n divided by epsilon. So we're happy. Otherwise, if opt is longer than that, so opt is much longer than the diameter. So it's making a lot of zigzag in its period, right? It's very long compared to the diameter. Then what do we do? And let's now focus on this case. So what we would like to do is that for any subgraph G prime in our decomposition that we obtain, if opt intersect G prime is not small with respect to the diameter of G prime, then we would like to patch opt, meaning that we would like to modify opt into a new solution that is not much more expensive, but that has nicer properties. So what does it mean? We show that there exists opt prime near optimal. We'll see what it means, but with small diameter compared to G prime, because now that will satisfy. Then we can work only with G prime and we'll be happy. So basically what we want to do is that the patch case shows us that there exists an opt prime that is near optimal. And that means that, I can just work with the opt prime from the beginning, and then I'm very happy because at any time when I pick this partition, I have small number of crossings. So let's look at this beautiful pizza defined by the gray area, which is the cluster of the subgraph I'm looking at, and the black curve, which is the opt solution. And let's say that opt is not short in the subgraph, meaning that the diameter of the subgraph is much smaller than opt inside the subgraph. Okay, so let's pick an arbitrary vertex on opt, this vertex here, 0. And let's work on opt on the black edges, and we increment the counter, and we don't increment the counter when we are outside. We only increment the counter when we are working on opt inside the gray area, inside the cluster. And as soon as we have traversed something that some epsilon log n over epsilon times the diameter of the cluster, so that this segment inside the cluster is short with respect to the diameter, is small with respect to the diameter, it's at most log n over epsilon times the diameter. Then I mark this vertex and I reinitialize my counter and I start walking again up to the next point where I mark this vertex and I start walking again. And then I'm going to add the shortest path from each of the marked vertex to the original vertex. So what do we have? We have that the length of each segment between consecutive marked vertices is at most log n over epsilon times the diameter of the gray area. So each segment that I'm considering like this, each path like this is small. Also note that the shortest paths are very small because they are at most the diameter, and we know that the diameter is small compared to the whole opt inside. So what we are doing here is that we are adding this path, the path I have drawn before, to opt. So I'm making a bigger subgraph that I'm going to decompose into cycles again. So what we did is that we have this now purple cycle whose total length is small with respect to the inside G, inside the G prime, this subgraph G prime, the length of the purple subgraph is small. Same thing for the green subgraph. Inside the gray area, the green subgraph is small. Same thing for the red part. And because the diameter is so small compared to the length of opt inside, adding these shortest paths from R to these marked vertices only add an epsilon over log n fraction of the length of opt inside. So here, this new subgraph that I'm creating right now only increases in length by 1 plus epsilon over log n times the length of opt inside. So it's not very much longer. And that's our patching. That's how we modify opt. Of course, this is only for the analysis. This is not happening on algorithm because we don't know opt. But what I'm trying to do is I'm trying to say that there exists a good opt. And that's how we build a good opt for the analysis. Okay, so now we apply this patching procedure for each subgraph. So we start at the top. For each part that doesn't satisfy this thing, we apply the patching procedure I told you, and then we recurse on the part that we have computed with the delta bounded partition. The depth of the recursion without loss of generality can be made order log n. So because we increase by an epsilon over log n factor for a given subgraph, the length of opt inside the subgraph, each time we patch, the total length of all the subgraph at the end, the entire subgraph at the end, is at most 1 plus epsilon times the total length of opt. This is just because we only increase a little bit by a little bit at each level, and there are only log n levels. Okay, so that's the first property. Second property is that now we are just adding more edges to opt, right? We are only adding this path to opt. So that's good because we are actually cutting more edges. So the only thing we are doing is that we are cutting even more demands than opt, because points that were, for example, in this part here and that part here, they were not separated by opt, but now we have added this path. So in the primal, it corresponds to adding a cut between these 2 points, and so now it breaks the demand. So we are happy because the demand split only increases. And now we have the property that each individual subgraph, of course, not the total subgraph, but if I just focus on the green or focus on the purple or focus on the red, it's short by definition inside G prime. The length of the edges of the green subgraph inside G prime is small with respect to the diameter of G prime, at most epsilon times log n, of 1 over epsilon times log n times the diameter of G prime. Okay, so what does it mean? 1 plus 2 implies that we have only increased the total length by 1 plus epsilon, and the demand only increased. So the collection of cycle, if we look at the pieces that are split by the collection of cycle, it's at most 1 plus epsilon. The total sparsity is at most 1 plus epsilon times higher. So this is good. We have that 1 plus 2 is a good solution for our problem. Okay, and that's how well we cut a pizza, because we know that by the modularity of the objective, given a collection of cycles of total length L and separating a demand of delta, which is what we have here, let's say, there exists one cycle in the collection that has sparsity at most L over delta. So if you have a total collection of cycles that has total sparsity x, then there is a cycle by average argument that has sparsity at most x. So we can pick one of them. So here is our pizza, and now we can cut one part of our pizza, which is a near optimal solution. So we are happy because we don't need to work with all these cycles that we have created. We can only work with one of them, and this one is near optimal. And that's the structural result we prove in this paper, is that because the total length of the cycle is 1 plus epsilon times the total length of opt, and the cycles, the collection of cycles separate the demand that is at least the demand of opt, then 1 plus 2 plus this property that I just told you tells you that there exists one cycle C star or sparsity at most 1 plus epsilon times the sparsity of opt in this collection. And the third property that I showed you shows you that I proved shows you that C star, all of them, actually all the cycles on the collection, but C star in particular, is small for each subgraph of the decomposition because that's how we built it. So now the structural result in picture tells us that there exists a cycle C star that has the desired property that, you know, at each level, the number of edges crossing the partition is only log n over epsilon. So our approach in summary is very simple. It just says that, okay, compute a hierarchical decomposition as follows: compute a diameter G over 2 bounded partition pi, P, then for each part of P, diameter G over 4, and so on, and you recurse for log n steps. And, you know, the good case was if C star is at most log n over epsilon times the diameter, then we know that the number of crossing in expectation is log n over epsilon. So that was the good case, and the else case cannot happen anymore because of our patching procedure. There is one challenge that I'm hiding under the rug right now, which is that the number of crossing is only bounded in expectation, which means that we could be unlucky, and because we are doing it many, many times, because we are doing it at each level, there is a reasonable probability that the number of crossing is going to be high at some point. We will get unlucky, not because the length of C star is long, but just because we chose the wrong vertex, and since we don't know up, we might get into trouble. This led us to introduce the notion of non-deterministic hierarchical decomposition, which essentially says that we pick a few hierarchical diameter delta bounded partition at each level, and we'll use the Shirley-Adams LP to help us choose the right one. That adds another layer of technicality that we have to handle in the paper, and that I'm not going to describe right now. But for the general picture, if you believe in your luck, you don't need to look at that right now. Okay, so the overview of the whole approach is the following: we have opt, we have this hierarchical decomposition, and we know that this decomposition is nice. There is a 1 plus epsilon approximation that has few number of edges crossing the paths at each level. So we are happy. And now we can use we have this decomposition that really behaves like a bounded tree-width graph, in a sense, because we know that the number of vertices for which there is one edge crossing the partition is only log n over epsilon. So at most, so it's really behaving like a bounded tree-width graph. Of course, we don't know exactly what is the who are the vertices with the edges, but we can kind of guess it as we go. The issue is that if we had the dynamic programming algorithm for non-uniform sparsest cut, it would be very easy to conclude right now. There would be a dynamic program that I will spend like 5 minutes explaining, but at the end, I think you would be convinced. Now we have to deal with bounded tree-width graph, and the way we deal with bounded tree-width graph is using the Gupta-Talwar Whitmer paper, which tells us that we need to use a linear program to solve the problem, and that's what I'm going to describe right now. So in a few minutes, so what we have is a decomposition into different pieces, and we know that there are a few crossing in opt, and we have different levels. So what we are essentially, again, hiding some details under the rug because there are many partitions at each level because of this expected number of crossing, and we have to make it high probability. But essentially what we're doing is that for any pair of bottom subgraph, like a leaf subgraph here, we consider all the possible choice of crossings over all possible parents between these two subgraphs. and they're only like, log squared n over epsilon roughly. So we can guess how many crossings there are, and what we want is a variable that indicates that represents that will be representing, when we find a solution, the convex combination of edges crossing these at each level. And this we have for all pairs of leaf clusters. And that basically tells us that, in the Shirley Adams LP, there is like the edges crossing at the top is really coming from a convex combination of solution of choices for these log n crossings. So that gives us like a quasi-polynomial size LP that we can solve. And we round it this way. So we look at the possible crossing at the top level, and because of the variables that I explained that are going up to the root, we have a convex combination of different edge crossings. And so we can simply round it by picking one of these combinations, and the rounding of the edges on the weight of the edges chosen gives us that, in expectation, we are doing, in terms of the length of the edges chosen, we are doing as good as opt. And then based on that, we can now proceed to the leaves or to the children, to the descendant of that top root cluster, and find the edges of opt crossing at this level, at this descendants, based on conditioning on what we have chosen for the ancestor. Of course, we are not conditioning on what we will choose here, or like there is no ordering of these vertices, but we can choose based on what happened to the ancestor. And that gives us that the cost we are going to find is as good, because we have variables for each pass from each green subgraph to the root. That gives us that the choices we're going to make for the length at each level is in expectation optimal. The issue is that we may not separate exactly the optimum demand between different bags, between different subgraphs, because when we are rounding, for example, for this subgraph, it's independent from what we are doing here, and we may not be rounding the right way, not optimally, but we can show that it's within a factor of 2 using the Gupta et al. With paper. Okay. So our result, the summary, is a 2 approximation algorithm for planar graph with a running time of n to the polylog. And there are a few open questions. So one natural open question is obtain a polytime, right? Like this is only quasi-poly, and it would be nice to obtain a polytime constant factor approximation. And the challenges are, so first challenge, I think, is to remove the dependency in log n in our patching process, because for now, we have a log n edges crossing, and these edges can be anywhere. So essentially it's n to the log n choices for finding these log n edges. So that's one bottleneck for sure. And then the second one is perhaps that we need to speed up as well the R1 approximation for 3-width T graph that has a running time for now, which is n to the T. And it's not FPT in that sense. It's not a clean FPT algorithm. And what we would like, I think what would be nice to have is R1 approximation for 3-width 3 graph that has like a running time, let's say, of 2 to the T and to the little and to the R1. That would be nice. Okay, so that's the 2 nice open questions. I think the second one is even independent of planar graph. So I'm writing for 3-width T graph, but planar 3-width 3 graph would be nice already. But of course, for general 3-width 3 graph, that's a good open question, I think. And of course, here there is also the question that this very famous question, which is that showing that the LP integrality gap for non-uniform sparsest cut is constant will imply that planar metrics embed into L1 Euclidean space with order-1 distortion. And it's a conjecture, it's an important conjecture. Of course, we are far from answering that question. We show that Shirley-Adams-based LP has order-1 integrality gap, indeed. But it's a sophisticated LP, and it doesn't imply anything for L1 embeddings. It implies some stuff for some weird embeddings coming from our Shirley-Adams LP, but it's not that interesting, I guess. And making progress toward the levels can be, like, the technique we developed can be useful for that. I think one key result to obtain along this line, if we want to use our framework to go there, is to show that the standard LP has constant integrality gap on tree-width T graph, planar graph. And this is not known. So I guess showing, yeah, constant, even this constant could be a function of T, but showing that for tree-width T planar graph would be interesting. And solving the above challenge would also help, I think. But one is definitely an important piece of the puzzle, probably. And I'll thank you for your attention, and happy to chat with you at the poster session.